If you could take every atom in the observable universe and compress it all into a single point, the result would barely fill a thimble. Every star, every planet, every moon, every grain of dust, every molecule of gas drifting between galaxies, every atom that has ever been part of anything at all, including every atom that has ever been part of a living thing, compress it all, and it fits in a thimble. The rest is empty, has always been empty, will be empty long after the thimble has dissolved. And somewhere inside that emptiness, you appeared by accident. This is the story of that accident. How nothing became something, why it almost did not. Why the forces arrayed against your existence were so overwhelming that the word improbable does not begin to cover it. And why, eventually, the emptiness will take back everything it temporarily lent. We will go slowly. This story deserves patience. It has been building for 13.8 billion years, and it ends in a silence so complete that time itself stops having anything to measure. The least we can do is take our time with it. The emptiness was here before us. It will be here after. And for one brief, impossible moment in between, it dreamed. The universe is almost entirely nothing. This is not a poetic exaggeration. It is not a metaphor designed to make you feel small. It is a precise, measurable, quantifiable fact about the physical world. When cosmologists calculate the average density of matter in the observable universe, they arrive at a number so close to zero that our everyday vocabulary has no honest way to describe it. Roughly 1 atom per cubic meter. One single hydrogen atom alone in a box the size of a house. Now imagine 1 billion of those boxes stacked together. That is the universe's average. 1 atom per cubic meter. You are surrounded right now by matter so dense it seems solid. The chair you sit on, the floor beneath it, the atmosphere pressing down on you, the walls holding the room together. This feels like the normal state of things. It is not. It is one of the rarest conditions in the observable cosmos. Almost everywhere in the universe, for almost all of its history, nothing has existed but cold, dark emptiness stretching in every direction without end. Start here. Start with the scale. The nearest star to our Sun is Proxima Centauri, 4.2 light-years away. A light-year is the distance light travels in a year, moving at roughly 186,000 miles per second. In 1 year, a photon of light covers about 5.9 trillion miles. 4.2 light-years is about 24 trillion miles. If you reduce the Sun to the size of a grain of sand and placed it on a table in front of you, the nearest neighboring grain of sand would be 6 kilometers away. Between those 2 grains, nothing. Not thin air, not faint gas, not darkness with occasional particles floating through it. For most of that 6 kilometers, genuinely and precisely nothing. The average density between stars in our galaxy is so low that the best vacuum chambers humans have ever built contain more matter than the space between stellar systems. And that is inside a galaxy. Inside a dense, crowded, star-filled spiral arm of the Milky Way. Between galaxies, the situation is more extreme by orders of magnitude. The distance from the Milky Way to the Andromeda Galaxy is about 2.5 million light-years. That is not 6 kilometers between grains of sand. That is 100,000 kilometers. In that space, there is essentially nothing. A thin plasma of ionized hydrogen, so sparse it is indistinguishable from perfect vacuum by any practical measure. A temperature of 2.7 Kelvin. The faint thermal afterglow of creation, too cold to drive any chemistry, too diffuse to clump, too uniform to do anything at all except drift apart as the universe expands. This is what the universe offers, almost everywhere, for almost all of time. Cold, dark, silent in every direction, but there is a structure to the emptiness, and it is worth understanding because it makes the emptiness more disturbing rather than less. The universe is not evenly empty. It has a skeleton. The matter that does exist is organized into an intricate three-dimensional web that cosmologists call the cosmic web, a network of filaments and nodes and walls surrounding enormous empty bubbles called voids. From far enough away, the cosmic web resembles the neural network of a brain, or the structure of a leaf's veins, or the foam of soap bubbles. It has a fractal quality, patterns repeating at different scales, structure emerging from the interplay of gravity and expansion over billions of years. But here is the key thing to understand about the cosmic web. The filaments, the galaxies, the clusters of galaxies, the bright nodes where filaments intersect these are not most of the cosmic web. They are the thin threads between the voids. The voids are the thing. The voids are the universe. The filaments are the decoration. The Boötes void is 330 million light-years across. Inside it, there are roughly 60 known galaxies where cosmological models predict there should be something like 10,000. It is not that the galaxies are hidden or dim or hard to detect. They are simply not there. A region of space so large that if our Milky Way sat at the center of it, we would not have discovered any other galaxy until the 20th century. The nearest galactic neighbor would have been outside the void entirely. Our astronomers, pointing telescopes at the sky in every direction, would have seen nothing for 165 million light-years in every direction. Just emptiness. And the Boötes void is not unusual. The giant void in the constellation Cetus, the Eridanus supervoid, correlated with a striking cold spot in the cosmic microwave background. The KBC void, a vast underdensity that our own Milky Way sits inside, stretching across 1 billion light-years of space, making our local cosmic neighborhood emptier than average by a significant margin. These voids are not holes in the universe. They are the universe. The filaments, the galaxies, the stars, the planets, the life, those are the anomaly. The minority, the exception etched into the surface of something that was always, fundamentally, nothing. The James Webb Space Telescope has been peering deeper into the early universe than any instrument before it. And one of its consistent findings is that the early universe was more structured than models predicted, with filaments and voids forming earlier and more sharply than expected. The cosmic web has been the dominant feature of the universe since shortly after the Big Bang. There was never a period when matter dominated. Even in the first billion years, the web was assembling itself, and the voids were opening up, and the emptiness was already winning. Let us pause here and really sit with the numbers. Not rush past them. The numbers are the point. The observable universe is a sphere roughly 93 billion light-years in diameter. This is not the total size of the universe, which may be infinite. It is the portion of the universe from which light has had time to reach us since the Big Bang. A sphere 93 billion light-years across. 1 light-year is about 5.9 trillion miles. 93 billion light-years is roughly 5.5 times 10 to the 23 miles. Written out in full, that is 550 sextillion miles. If you drove at highway speed continuously without stopping, it would take you about 10 to the 26 years to cross the observable universe. The universe has only existed for 13.8 billion years, which is about 10 to the 10 years. You would need to have started driving 10 to the 16 times the age of the universe ago to have crossed the observable universe by now. Inside this sphere, there are roughly 2 trillion galaxies. 2 trillion is 2 times 10 to the 12. Each galaxy contains, on average, roughly 100 billion stars. 100 billion is 10 to the 11. Multiply 2 trillion galaxies by 100 billion stars, and you get 2 times 10 to the 23 stars. That is roughly the number of grains of sand on all the beaches and deserts of Earth. For every grain of sand on every beach, on every continent, there is roughly 1 star in the observable universe. Now, consider how much volume all those stars occupy compared to the total volume of the observable universe. The Sun has a radius of about 432,000 miles. Its volume is about 1.4 times 10 to the 27 cubic meters. A typical star is roughly this size. 2 times 10 to the 23 stars, each with a volume of about 10 to the 27 cubic meters, gives a total stellar volume of roughly 2 times 10 to the 50 cubic meters. The volume of the observable universe is roughly 4 times 10 to the 80 cubic meters. The fraction of the observable universe occupied by stars is therefore about 2 times 10 to the 50 divided by 4 times 10 to the 80, which is about 5 times 10 to the negative 31. That is 5/10 of a quintillionth of the volume. Stars, the brightest and most energetic objects in the universe, the things we see when we look at the sky, occupy less than 1 part in a quintillion of the observable universe's volume. Everything else is empty. And even within the stars themselves, most of the volume is empty. An atom is mostly empty space. The nucleus of an atom, where nearly all the mass is concentrated, occupies about 1/10,000th of 1% of the atom's volume. The rest is the space in which the electrons exist, governed by quantum probability distributions. If you scaled up a hydrogen atom so that the nucleus was the size of a marble, the electron's probable location would be in a sphere roughly a mile wide. Inside that mile, almost entirely empty. So when we say the universe is almost entirely nothing, we mean it at every scale we can examine. The universe as a whole is almost entirely the void between galaxy clusters. Each galaxy is mostly the void between stars. Each star is mostly the void between atoms. Each atom is mostly the void between the nucleus and the electrons. Matter, at every scale, is an exception to a rule of emptiness. The solidity you experience in everyday life is an emergent illusion produced by electromagnetic forces between electron clouds, the quantum exclusion principle preventing electrons from occupying the same states, and the electromagnetic fields of atoms pushing against each other when you press your hand against a surface. The surface you are sitting on is not solid in any deep physical sense. It is a network of electromagnetic forces so strong that you cannot push your atoms through the gaps between the atoms of the chair. But the gaps are there. The emptiness is there. At every scale, down to the smallest we can examine, the universe is mostly nothing. This is not a metaphor. It is a direct description of physical reality. The solidity you feel when you press your hand on a surface is an emergent illusion produced by electromagnetic forces and quantum exclusion, not by the presence of stuff. The stuff is almost entirely absent. What fills the universe at every scale from the cosmic web to the atom is the space between things. The things themselves are the anomaly. Matter is the impurity. Life is the further impurity. Consciousness is the most extraordinary and improbable impurity of all. Now add the invisible inventory. The atoms, the stars, the gas, the dust, everything you can see or detect with any instrument, make up roughly 5% of the universe's total energy content. 5%. The remaining 95% is divided between two things we cannot see, cannot touch, cannot directly detect and do not understand. Dark matter makes up about 27%. It does not emit light or absorb it, does not interact with electromagnetism, does not form atoms or molecules or anything we would recognize as matter. We know it exists because of its gravitational effects. Without dark matter, galaxies would fly apart. The stars on the outer edges of spiral galaxies rotate too fast to be held by the gravity of visible matter alone. Something else is providing the gravitational glue. That something is dark matter, and it outweighs all the visible matter in the universe by a factor of roughly 5-to-1. But it is invisible, inert, and indifferent to us in every way. The evidence for dark matter comes from multiple independent directions. Galaxy rotation curves. The observation that stars on the outer edges of spiral galaxies move faster than they should if only visible matter were present was one of the first strong indicators and was studied systematically by astronomer Vera Rubin in the 1970s. Gravitational lensing, the bending of light from distant objects by the gravity of foreground matter, shows that galaxy clusters contain far more mass than their visible stars and gas account for. The bullet cluster, formed by the collision of two galaxy clusters, shows visible gas being slowed by the collision, while a transparent halo of dark matter passed through without interacting, separating the two components in a way that can be directly imaged through gravitational lensing. The large-scale structure of the cosmic web itself, with its specific pattern of filaments and voids, matches theoretical predictions only if dark matter is present, as the gravitational scaffolding that shaped the web's formation. Before we go further, it is worth pausing to acknowledge something. How do we know any of this? How do astronomers measure the density of the universe, map the cosmic web, determine the size of the Boetes void, calculate the fraction of the universe made of dark energy? These are not trivial observations. They require building on centuries of accumulated scientific knowledge, and they are worth understanding, at least in outline, because they ground everything that follows in something real and measurable rather than speculation. The density of the universe is calculated by combining multiple independent lines of evidence. The cosmic microwave background, the faint thermal afterglow of the Big Bang that fills the entire sky at a temperature of about 2.7 Kelvin, carries imprinted in its slight temperature variations the initial conditions of the universe. By analyzing the statistical pattern of those variations with extraordinary precision, cosmologists can determine the total matter density, the dark matter density, the dark energy density, and the geometry of space. The results from the Planck satellite and earlier missions converge on the same picture. Ordinary matter is roughly 5% of the total, dark matter 27%, dark energy 68%. The existence of the cosmic web was first predicted, theoretically, and then confirmed observationally. The first maps of the large-scale structure of the universe, produced in the 1980s by surveys that measured the redshifts of thousands of galaxies to determine their distances, revealed a striking pattern of filaments, walls, and voids that matched the theoretical predictions of structure formation by gravitational collapse remarkably well. Subsequent surveys, increasingly ambitious in scope, have confirmed and extended this picture. The Sloan Digital Sky Survey mapped millions of galaxies and produced the most detailed three-dimensional map of the cosmic web ever assembled. The results are unambiguous. The universe is a web of structures surrounding enormous empty voids. The Boetes void was discovered in 1981 by astronomers Robert Kirshner, August Oehmler, Paul Schechter, and Stephen Schechtman, who were conducting a survey of galaxy redshifts They found a region of space covering about 3% of the sky in the direction of the constellation Boötes that was almost completely devoid of galaxies. Subsequent surveys have refined the estimate of its size and confirmed its emptiness. It is real. It has been measured from multiple independent angles with consistent results. The KBC void was identified in 2013 by Ryan Keenan, Amy Barger, and Len Cowie from Galaxy Counts in infrared surveys. The evidence suggests we live inside a region of below-average density, roughly 1 billion light-years across, and this underdensity may contribute to a tension between different measurements of the universe's current expansion rate, one of the most actively debated topics in cosmology today. The nature and composition of dark matter and dark energy remain uncertain in their physical identity, but their existence and their relative contributions to the universe's energy budget are not seriously in doubt among cosmologists. Dark matter's effects on galaxy rotation curves, gravitational lensing, and the formation of large-scale structure are well established. Dark energy's effects on the expansion rate of the universe have been confirmed by multiple independent methods, including Type Ia supernovae, baryon acoustic oscillations in the cosmic web, and the cosmic microwave background. What we do not know is what dark matter and dark energy physically are, not what they do. The picture of a universe dominated by emptiness is not a guess or a philosophical position. It is the well-supported conclusion of decades of observation with the best instruments humanity has built. The universe really is almost entirely nothing. The evidence is overwhelming and consistent. So if emptiness is the natural state of the universe, if the physics of dark energy drives everything relentlessly toward greater and greater separation, the question that demands an answer is this: why is there anything at all? This is not a rhetorical question. It is the deepest question in all of physics and philosophy combined. And the honest answer is that we do not fully know. But we have pieces of the answer, and the pieces are extraordinary. Before the Big Bang, there was no space, no time, not empty space, not dark space, not space waiting to be filled, no space of any kind. The concept of location did not exist. The concept of before did not exist in any meaningful sense because time itself had not yet begun. Physics, as we understand it, stops at the singularity of the Big Bang. The equations break down. We cannot peer past it. What we can say is this: the Big Bang was not an explosion into space. It was the creation of space. Space, time, matter, and energy all came into existence simultaneously in a state of extreme density and temperature, and have been expanding and cooling ever since. The observable universe today, all 46 billion light-years of it in every direction, was once compressed into a region smaller than an atom. Before that, smaller than a proton. Before that, smaller than anything we have a physical theory to describe. Quantum mechanics allows something extraordinary. In quantum field theory, the vacuum is not truly empty. Even in the absence of any particles, fields permeate all of space, and those fields fluctuate randomly at the quantum level. Virtual particles appear and annihilate in pairs, borrowing energy from nothing and returning it so quickly that the universe's energy accounting is never violated. The vacuum seethes with these fluctuations constantly, everywhere, in all fields, simultaneously. The leading hypothesis for the origin of the universe is that it began as a quantum fluctuation of this kind. Not in space, because space did not exist, but in whatever pre-geometric state preceded space. A fluctuation of the quantum vacuum that, instead of immediately annihilating, inflated, a bubble that did not pop. The one in a countlessly many chance event that produced a stable, expanding universe instead of a transient quantum ghost that vanished before anything could happen. The universe may be the one bubble that did not pop. In the first 10 to the negative 36 seconds after the Big Bang, something extraordinary happened. The universe expanded at a rate that makes the word fast meaningless. In a fraction of a second so small it has no name in everyday language, space expanded by a factor of at least 10 to the 26. The universe went from the size of a proton to the size of something roughly comparable to a grapefruit in a time so brief that light, traveling at the speed of light, would not have moved a single atom's width. This process is called inflation, and it is the best explanation physicists have for several otherwise puzzling features of the universe. The horizon problem. Why is the cosmic microwave background almost perfectly uniform in temperature across the sky, even in regions that could never have been in contact with each other at light speed? If you look in opposite directions in the sky, the regions you are looking at are separated by 93 billion light-years. Given that the universe is only 13.8 billion years old, light could never have traveled between those regions. They could never have been in thermal contact with each other. Yet they are at exactly the same temperature to within about 1 part in 100,000. How? Inflation answers this. Before inflation began, all these regions were in causal contact, close enough that thermal equilibrium was established. Then, inflation stretched space so dramatically that regions that were once in contact were flung to opposite ends of the observable universe. The uniformity is a memory of the brief, pre-inflationary epoch when everything was close together. The flatness problem. Why does the geometry of the universe appear so precisely flat, so close to the critical density that divides an open universe from a closed one? In standard cosmological evolution without inflation, any small deviation from flatness in the early universe would have grown dramatically over time. A universe that was slightly above critical density would have collapsed long before now. A universe slightly below critical density would have expanded too quickly for structures to form. Yet the universe today is flat to within measurement precision. Inflation solves this by stretching the geometry of space so dramatically that any initial curvature becomes negligible, just as the surface of a balloon appears flat when inflated to enormous size. But inflation did something else. Something that turns out to be essential to this story. The inflaton field, the quantum field driving the inflationary expansion, had quantum fluctuations of its own. These fluctuations were random, patternless, purely probabilistic. Quantum mechanics demands that any field have random fluctuations at the microscopic level, a consequence of the uncertainty principle. Under normal circumstances, these fluctuations are tiny and confined to subatomic scales. But during inflation, the exponential expansion of space stretched these quantum fluctuations to macroscopic and then cosmic scales, freezing them into the fabric of the early universe as variations in density before they could oscillate away. The result was a universe with slight variations in density distributed across all scales. Some regions ended up very slightly denser than average, perhaps 1 part in 100,000 denser. Some very slightly less dense. These differences were tiny, but they were real, and they were permanent, imprinted into the fabric of space-time by the expansion of inflation before anything could smooth them out. These density variations are what we observe in the cosmic microwave background. When we measure the tiny temperature fluctuations across the sky with instruments like the Planck satellite, we are reading the imprint of quantum fluctuations that occurred in the first 10 to the negative 36 seconds of the universe's existence. We are reading the original seed file from which everything else grew. Those seeds became everything. The slightly denser regions attracted more matter gravitationally. Over hundreds of millions of years, they collected gas, which collapsed into the first stars, which formed galaxies, which organized into the filaments of the cosmic web. The slightly less dense regions expanded faster than average and became the voids. The cosmic web, with all its filaments and all its emptiness, is the grown-up version of quantum noise in an inflaton field. The entire large-scale structure of the universe. Every galaxy, every star, every planet, every living thing traces back to quantum noise in an inflaton field during the first fraction of the first second of existence. Had the fluctuations been slightly different, had the inflaton rolled down its energy potential in a slightly different configuration, the resulting density seeds would have been different, more uniform, and no structures would have formed at all. The universe would be a perfectly smooth, perfectly featureless cooling gas forever, expanding silently and growing colder without ever producing anything interesting. More extreme, and everything would have collapsed into primordial black holes before stars ever formed. The laws of physics themselves are, in this framework, not necessary truths. They are accidents. The physical constants, the strength of gravity, the mass of the electron, the charge of the proton, emerged from the inflaton's behavior in the first moments of existence, from the specific point in its energy terrain where inflation ended. Different inflaton dynamics would have produced different constants, different forces, different physics, different universes in which nothing we recognize would exist or could exist. Our laws of physics are the accident of where the inflaton landed. There is a further consequence of inflation that some physicists take seriously and that is worth pausing on. If the inflaton field had slightly different properties in different regions during inflation, if it stopped inflating at different times in different places, those regions would have gone on to develop different physical laws, different constants, different physics. This is the multiverse of eternal inflation. A vast collection of bubble universes, each one the product of a local end to inflation in some region of an inflating background space, each one with its own physical constants drawn from the full range of possible constants that the inflaton field allows. Most of these universes would have constants incompatible with complexity, empty, sterile, cooling forever with no stars, no chemistry, no possibility of anything like life. Our universe would be one of the rare ones where the constants happen to fall in the narrow range that permits complexity. We exist here because we can only exist in the rare bubbles where the conditions are right. This is the anthropic selection argument applied to the multiverse. Whether the inflationary multiverse is real is not known. It makes predictions that are currently impossible to test, but it provides a coherent framework within which the improbability of our universe's physical constants becomes a selection effect rather than a genuine puzzle. Not a solved puzzle, a reframed one, but that is only the first accident. There is a second one, and it is almost more improbable. In the first second after the Big Bang, the universe was filled with an extraordinary hot plasma of matter and antimatter in almost exactly equal quantities, protons and antiprotons, electrons and positrons, quarks and antiquarks. For every type of matter particle, a corresponding antimatter particle existed in roughly equal numbers. When a particle meets its antiparticle, they annihilate each other, converting their combined mass into pure energy in the form of photons. If the quantities had been exactly equal, they would all have annihilated. Every particle of matter and every particle of antimatter would have found a partner and converted to energy. The universe would contain nothing but photons. No atoms, no chemistry, no stars, no planets, no anything. A universe of light. But the quantities were not exactly equal. For every 1 billion antimatter particles, there were 1,000,000,001 matter particles. A difference of 1 part in a billion. An asymmetry so tiny that explaining it fully remains one of the great open problems in modern physics. The standard model of particle physics predicts a process called CP violation that should produce some matter-antimatter asymmetry. But the predicted amount is far too small to account for the observed asymmetry. Something beyond our current understanding produced this particular imbalance. To appreciate how remarkable this is, consider what it means numerically. In the first second after the Big Bang, the universe contained on the order of 10 to the 80 protons worth of energy in the form of a hot plasma of quarks, antiquarks, and gluons. For every 10 to the 80 antiprotons that formed, there were 10 to the 80 plus 1 protons. The total number of matter particles exceeded the total number of antimatter particles by about 1 in a billion. The extra matter particles, the ones with no antimatter partner to annihilate against, numbered something like 10 to the 80 minus 10 to the 71, which simplifies to roughly 10 to the 71. Those 10 to the 71 surplus protons are everything we see when we look at the universe. Every galaxy, every star, every planet, every molecule, every atom of every living thing. 10 to the 71 protons in a universe that started with 10 to the 80 protons worth of energy is less than 1/1000th of the original inventory. We are the rounding error. We are what was left after a near-perfect cancellation. Had the cancellation been perfect, had the ratio been exactly 1:1, the universe would contain photons and neutrinos and nothing else. No matter, no structure, no stars, no planets, no chemistry, nothing. The reason the cancellation was not perfect is unknown. There are theoretical models that could produce the observed asymmetry through various mechanisms. Leptogenesis, where an asymmetry in leptons is converted to a baryon asymmetry. Electroweak baryogenesis, where the phase transition as the universe cooled through certain temperatures produced the asymmetry. Other exotic mechanisms involving physics beyond the standard model. None of these are confirmed. None of them have been tested experimentally in a way that establishes which, if any, is responsible for the asymmetry we observe. We know the asymmetry exists. We can measure it from the ratio of photons to baryons in the universe today. We cannot explain it, and without it, we do not exist. The billion pairs annihilated. A billion photons of energy were released for every particle pair that met. And the one leftover particle in every billion, the orphan, with no antimatter partner to annihilate against, survived. Everything you have ever seen is made of those orphans. Every star in the sky, every planet, every molecule of air you have ever breathed, every atom in your body. You are not just made of star stuff, as the saying goes. You are made of antimatter rejects. You are the leftover, the rounding error, the 1 in a billion accounting error that the universe never got around to correcting. If the asymmetry had been slightly smaller, not enough matter would have survived to form galaxies. If it had been slightly larger, the photon-to-baryon ratio would have been wrong, and the chemistry of the early universe would have been different in ways that might have prevented stars from forming. It had to be very close to what it was, by accident. Think about what these two events, taken together, actually mean. The universe began from a state that may have been a quantum fluctuation of the pre-geometric vacuum. That fluctuation inflated, driven by a field whose quantum noise determined the large-scale structure of everything that followed. And then the matter that formed in the first second survived only because of an asymmetry of 1 part in a billion whose origin remains unknown. Two extraordinary contingencies in the first second of time. Each one independently required, neither one explained. And they bring us immediately to a third, the constants. The accidents of inflation and baryogenesis gave us a universe with matter in it. But matter is not enough. Matter has to do something. It has to form structures, produce energy, enable chemistry, allow the emergence of complexity over time. Whether matter can do any of these things depends entirely on the values of the fundamental constants of physics. And those constants, as we have seen, are themselves accidents. But the depth of the accident is more extreme than almost anyone expects when they first encounter it. There are a handful of numbers that define the physics of our universe, the strength of the strong nuclear force which holds atomic nuclei together, the strength of the electromagnetic force which governs how atoms bond and how light interacts with matter, the ratio of the electron mass to the proton mass, the gravitational coupling constant which determines how strongly gravity pulls, the cosmological constant which determines how strongly dark energy pushes. Each of these has a value that sits in a narrow range that permits the existence of complex chemistry, stable atoms, and long-lived stars. Consider the strong nuclear force. It holds the quarks inside protons and neutrons together, and it holds protons and neutrons together inside atomic nuclei. If the strong force were about 2% stronger than it is, protons would bind to each other directly, and all the hydrogen in the early universe would have converted to helium and heavier elements in the first few minutes. There would be no hydrogen left. No hydrogen means no water. No hydrogen means no organic chemistry, which is built on carbon-hydrogen bonds. No hydrogen means no stars that burn for billions of years on a hydrogen fuel supply, giving planets time to cool and chemistry time to complexify. The universe would be a place of helium and heavier elements with no long-lived stars and no water chemistry and no biology of any kind we can imagine. If the strong force were about 5% weaker, deuterium would be unstable. Deuterium is the bridge in the fusion chain that powers stars. Without stable deuterium, the fusion chain cannot proceed. No stable deuterium means no stellar fusion, no starlight, no energy to drive chemistry on planetary surfaces. The universe would be full of hydrogen gas that never ignited, cooling slowly into a dark, cold, sterile soup for the rest of time. Consider the cosmological constant, the value that determines the strength of dark energy. The measured value is extraordinarily small. It is something like 10 to the negative 120 in natural units, meaning it is about 1 followed by 120 zeros times smaller than the naive prediction of quantum field theory for what it should be. Physicists call this the cosmological constant problem, and it is considered one of the greatest unsolved problems in physics. We do not know why it is so small. But here is the key point. If the cosmological constant were larger by a factor of roughly 1 followed by 120 zeros, the universe would expand so rapidly that matter could never clump together. Dark energy would overwhelm gravity before the first stars formed. The universe would expand into a featureless low-density void before anything interesting could happen. If the cosmological constant were negative and of similar magnitude, the universe would collapse back on itself before the first second of existence ended. The actual value sits in a range, relative to what it could have been, of about 1 part in 10 to the 120. That is a precision of 1 part in a number so large it has no name in everyday language. Written out, it would be a 1 followed by 120 zeros. That is the target the cosmological constant had to hit for a universe like ours to be possible. Consider the electromagnetic force. It determines how strongly charged particles attract and repel each other, and it is the force responsible for the existence of atoms, molecules, and chemistry. The electromagnetic force is what holds electrons in orbit around atomic nuclei. It is what determines the energy levels of those electrons and therefore the wavelengths of light that atoms absorb and emit. It is what governs chemical bonding and therefore everything that chemistry can build. If the electromagnetic force were significantly stronger, electrons would be bound more tightly to nuclei. The energy gaps between quantum states would be larger, and chemical reactions would require more energy. The rich and varied chemistry of carbon compounds, the chemistry of life, depends on a specific range of electromagnetic force strength that allows for a large number of similar energy states and therefore a large number of accessible chemical reactions. Too strong, and chemistry becomes constrained to a few high-energy reactions. Too weak, and atoms cannot hold themselves together. Consider the ratio of the electron mass to the proton mass. The proton is about 1,836 times heavier than the electron. This ratio seems arbitrary, but it matters. The fact that electrons are so much lighter than protons is what allows atoms to have well-defined quantum states with sharp spectral lines. It is what allows the mathematics of quantum chemistry to be tractable, to have a clear separation between the fast electron dynamics and the slow nuclear dynamics. If the electron were comparable in mass to the proton, the quantum states of atoms would be far more complicated and the stable chemical bonds of organic molecules might not exist. The specific mass ratio we observe is in the narrow range that permits the chemistry of life. These constraints are not independent. They interact with each other in complex ways. The viable range for the strong force depends on what value the electromagnetic force has. The viable range for the cosmological constant depends on when inflation ended and what density of matter resulted. The full space of viable physics, universes with any interesting chemistry at all, is a tiny island in the enormous parameter space of possible physics. Change any one constant by a small amount in almost any direction, and you fall off the island into a universe that is forever empty, forever sterile, forever dark. The question this raises is unavoidable. Why are the constants what they are? 3 answers are possible, and none of them is comfortable. The first answer is that we got lucky. The constants are what they are by pure chance, and we are here because the constants happen to permit our existence. This is technically possible. It is deeply unsatisfying because it provides no explanation. It simply says, it is this way, and we are here because it is this way, and there is nothing more to say. It assigns the most extraordinary apparent coincidence in the history of science to pure chance with no underlying reason. The second answer is the multiverse. If there are vastly many universes, each with randomly determined physical constants, then by the logic of selection effects, we can only exist in one of the universes where the constants permit our existence. We are not in a typical universe. We are in one of the rare ones, where the constants happen to allow complexity. The multiverse makes the apparent fine-tuning a selection effect rather than a genuine improbability. But the multiverse cannot currently be tested. It makes no predictions we can verify with any technology we can imagine building. It is a framework that solves a philosophical problem by invoking an infinite number of unobservable realities. This may be true. We have no way to know. The third answer is that there is something we do not yet understand, some deeper physical principle that forces the constants to be what they are, some equation whose solution uniquely specifies the values we observe. This would be the most satisfying answer scientifically. String theory's space of possible vacua suggests that no such unique solution exists, that the constants are genuinely variable across different possible realizations of the theory. But string theory is itself unconfirmed. We are waiting, and the wait may be very long. What we are left with, in the meantime, is this. You exist because gravity is strong enough to form stars, but weak enough not to collapse the universe. You exist because the strong force holds nuclei together without fusing all hydrogen into helium. You exist because the cosmological constant is extraordinarily small, for reasons unknown, allowing dark energy to be weak enough that gravity could form galaxies. You exist because the electromagnetic force is exactly strong enough to allow stable atoms and complex chemistry. Every one of these parameters had to be what it is. Change any of them by a small amount in almost any direction, and you do not exist. Change most of them, and nothing interesting exists anywhere. We are inside a room whose temperature is perfect, whose air is breathable, whose gravity is gentle. And we cannot tell whether someone built the room for us, or whether we are simply the kind of thing that can only exist in rooms like this. And this particular room came into existence by a chain of accidents so improbable that every metaphor for improbability we have ever invented falls short of capturing it. Even with the physical constants perfectly placed, even with matter surviving and gravity working and stars able to form, the universe had no obligation to produce life. The gap between physics and biology is not a small gap. It is the largest gap in all of science. And bridging it required a sequence of contingencies so specific that we still cannot fully account for how they converged. It is worth appreciating what biology actually requires before we discuss how it got here. Life, as far as we know it, is built on carbon chemistry. Carbon is uniquely suited to forming the complex molecules of life because of its chemistry. It can form 4 stable bonds simultaneously. It can bond with itself to form long chains and rings, and it can form stable bonds with hydrogen, oxygen, nitrogen, phosphorus, and sulfur, the other main elements of biology. No other element has this combination of properties. Silicon, which sits directly below carbon on the periodic table and is far more abundant on Earth, cannot form the same variety of stable molecules at biological temperatures. Carbon is the one element in the periodic table that can serve as the backbone of the enormously varied molecular structures biology requires. But carbon does not exist in a universe that contains only hydrogen and helium. Carbon has to be forged. It has to be created inside stars by the triple alpha process, in which 3 helium nuclei fuse together to form a carbon nucleus. This process requires a specific resonance in the energy levels of carbon and its precursor, beryllium. A resonance that Fred Hoyle predicted must exist in order for stars to produce carbon at all, before the resonance was experimentally confirmed. The specific energy level of the carbon nucleus is not derived from first principles by any theory we have. It is simply what it is. Had the resonance been slightly different, carbon production in stars would have been far less efficient, and the universe might have far less carbon in it. The universe that contains carbon-based life requires that the carbon nucleus have an energy level within a specific range. That energy level is an accident of the nuclear physics, governed ultimately by the constants of the strong and electromagnetic forces, which we have already seen are accidents themselves. The first stars were nothing like the stars we see today. They formed roughly 200 million years after the Big Bang from clouds of hydrogen and helium, the only elements that existed at that point. No carbon, no oxygen, no nitrogen, no iron, no calcium, no phosphorus. None of the elements that biology requires. The first stars were enormous by modern standards, hundreds of times the mass of our Sun, burning through their fuel in a few million years and dying violently. They were too short-lived and too massive to have planets worth considering. There was no chemistry happening around the first stars that could lead to life. The universe, in its early stages, was sterile. But those first stars died. And in dying, they did something essential. In the core of a massive star, temperatures reach high enough to fuse helium into carbon, carbon into oxygen, oxygen into silicon, silicon into iron. Each fusion step builds heavier and heavier elements, releasing energy at each step until iron is reached, at which point fusion consumes more energy than it releases, and the process stops catastrophically. The iron core collapses in a fraction of a second, and the resulting supernova explosion disperses the heavy elements forged during the star's life into the surrounding interstellar medium. The first generation of massive stars seeded the universe with carbon, oxygen, nitrogen, and dozens of other elements. The second generation of stars formed from gas enriched by those first stellar deaths. They too lived and died, enriching the interstellar medium further. Each generation of stellar evolution added more heavy elements to the cosmic inventory. By the time the Milky Way was a few billion years old, the interstellar medium was rich enough in heavy elements to form rocky planets. The carbon in your cells was forged in the cores of stars that died before the solar system formed. The oxygen you are breathing right now was scattered into the galaxy by stellar winds and supernova explosions billions of years ago. The iron in your blood was forged in the final moments of a massive star's collapse. A star that died perhaps 8 or 10 billion years ago, long before the sun ignited, and whose atoms drifted through the galaxy until they were swept up into the molecular cloud that eventually became the solar system. You are made of stellar corpses. You are a recycling of ancient stellar material. You are what happens when the products of stellar alchemy sit in a warm, shallow ocean for a few billion years. But this required that the first stars existed at all, that they were massive enough to fuse heavy elements, that they died violently enough to disperse those elements rather than locking them up in stellar remnants, and that the universe survived long enough for multiple stellar generations to enrich the interstellar medium before the sun formed. All of this happened. The physical laws permitted it at each step, but none of it was required. The timing matters enormously. The sun formed about 4.5 billion years ago, roughly 9 billion years after the Big Bang. By that point, the Milky Way had already processed several generations of stars, enriching the interstellar medium with carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements. If the sun had formed earlier, in the first few billion years of the universe when heavy element abundances were lower, the rocky planets that formed around it might have lacked the chemical complexity needed for the biochemistry of life. If it had formed much later, the galaxy would have been further along in its stellar evolution, but the star formation rate was already declining, and the conditions for a stable solar system might have been different. The sun also had to be the right kind of star. Not too massive, which would have meant a lifespan of only tens of millions of years rather than 10 billion. Not enough time for evolution to produce complexity. Not too small, which would have meant a red dwarf with a habitable zone so close that tidal locking would be a concern. The Sun is a G-type star, middle mass, with a lifespan long enough to allow the full arc of biological evolution from the first cell to the first mind. The specificity of this requirement, the window of stellar masses that allow complex life, is another filter in the chain. Every step of stellar evolution that produced the elements in your body required stars to form, burn, and die in the right way at the right time. You are not just made of star stuff in a poetic sense. You are physically assembled from the nuclear waste of stars that no longer exist. Waste that was scattered into space by the violence of their deaths, gathered into a new star by gravity, organized into planets by the physics of accretion, and then transformed by chemistry and time into the molecular structures of life. You are the universe's way of recycling its dead stars. Then there is the question of the planet. Before we even reach the question of a specific rocky world in a specific orbit, there is the question of where in the galaxy the solar system formed. Not every region of the Milky Way is equally hospitable to the development of complex life. Astronomers have proposed the concept of a galactic habitable zone, a band of the galaxy at a certain range of distances from the center where the conditions are most favorable. Near the galactic center, the density of stars is very high, which means frequent, close stellar encounters that could disrupt planetary orbits. It also means higher rates of supernovae, which release intense radiation capable of stripping planetary atmospheres and causing mass extinctions. The center of the galaxy is also home to the supermassive black hole Sagittarius A star, whose periodic bursts of activity would sterilize nearby planetary systems. Life near the galactic center faces threats that life in the outer galaxy does not. In the outer reaches of the galaxy, the density of heavy elements in the interstellar medium is lower. Fewer stellar generations of recycled material through supernovae in the outer galaxy, so the heavy element abundance needed to form rocky planets and the molecular complexity needed for biology is lower. Rocky planets in the outer galaxy may be smaller, with less of the heavier elements needed for the interior geochemistry that drives plate tectonics and magnetic field generation. The solar system sits in a relatively quiet, moderately enriched region of the galaxy at about 25,000 light-years from the center in a minor spiral arm, not too close to the radiation and chaos of the center, not too far out to have sufficient heavy elements. In the galactic habitable zone, at least as far as we currently understand it, a rocky planet in the habitable zone of a stable star is necessary but far from sufficient for life. The habitable zone is the orbital region where liquid water can exist on the surface, not too hot, not too cold. Earth sits comfortably in this zone, but an Earth-like planet requires much more than a comfortable orbit. It requires a magnetic field strong enough to deflect the solar wind, which would otherwise strip the atmosphere away over millions of years. Earth's magnetic field is generated by the motion of liquid iron in its outer core, a consequence of its size, its composition, and its thermal history. A somewhat smaller planet might have cooled too quickly, solidifying its iron core and losing its magnetic dynamo. A somewhat larger one might have retained too much internal heat, driving different geological processes. The specific size of Earth matters. It requires plate tectonics to cycle carbon between the atmosphere, the ocean, and the rocks. Without the carbon silicate cycle driven by plate tectonics, atmospheric carbon dioxide would build up over millions of years from volcanic outgassing, producing a runaway greenhouse effect. Or it would be drawn down too efficiently by chemical weathering, producing a frozen world. Plate tectonics regulates the carbon cycle and keeps the surface temperature stable over geological timescales. Mars does not have plate tectonics. Venus does not have plate tectonics. Earth has plate tectonics, apparently because of its specific size, internal temperature, and composition. It requires a large moon. The moon stabilizes Earth's axial tilt, keeping it within a narrow range over geological time. Without the moon's gravitational stabilization, Earth's axial tilt would wander chaotically between nearly 0 and 90 degrees over millions of years producing wild swings in climate that might prevent complex life from ever getting a foothold. The Moon exists because of a specific, improbable collision between the proto-Earth and a Mars-sized impactor called Theia early in the solar system's history. Had Theia not struck at that specific angle and velocity, no Moon would have formed, or a much smaller one would have formed, and Earth's axial stability might have been compromised. It requires a gas giant in the outer solar system to act as a gravitational shield, capturing or deflecting comets and asteroids that would otherwise bombard the inner planets continuously. Jupiter's gravity has cleared much of the outer solar system of debris. Without Jupiter, the rate of large impactors striking Earth might be orders of magnitude higher, preventing the stable geological and biological epochs that allowed complex life to develop. It requires a stable star with a long enough lifetime. The Sun is moderately massive, burning steadily for about 10 billion years. More massive stars burn faster and die sooner, not giving planetary chemistry enough time to produce complexity. Less massive stars, the abundant red dwarfs, present different challenges. Their habitable zones are very close to the star, making planets likely to be tidally locked with one face always toward the star and one face always away, creating extreme temperature differences. Red dwarfs also emit frequent, powerful stellar flares that could strip the atmospheres of close-in planets. Whether life can exist around red dwarfs is an open and actively debated question. Stack these requirements together. The right position in the galaxy, a star of the right mass and type, the right generation of stellar evolution for heavy element abundance, the right orbital position for liquid water, the right planet size for magnetic field and plate tectonics, the right collision history to produce a large stabilizing moon, the right outer solar system architecture to reduce bombardment. Every one of these factors has to fall in the right range simultaneously. None of them follows from the others. Each is a separate lottery ticket that had to come up correct. And this is before we even get to life itself. The origin of life, the transition from non-living chemistry to self-replicating molecules, is the deepest mystery in all of biology. We know it happened on Earth. We know it happened at some point in the first billion years of the planet's existence, because microbial fossils and chemical signatures of life appear in rocks around 3.5 to 3.8 billion years old. But we do not know how it happened. No laboratory experiment has ever replicated the origin of life from scratch, despite decades of effort and enormous scientific investment. The gap between even the most complex known chemistry and the simplest known living cell is enormous. The simplest living organism we know of is a single bacterial cell. Even the simplest bacterium contains thousands of genes, millions of atoms arranged in precise three-dimensional structures, hundreds of molecular machines, each performing specific tasks, and a metabolic network of hundreds of interacting chemical reactions all running simultaneously. The coordination required to keep a living cell alive, to replicate it faithfully, to respond to its environment, to repair damage, is staggering in its complexity. And all of this complexity has to function together, all at once, from the first moment of the cell's existence. A cell that is only 90% functional is not 90% alive. It is dead. The leading hypothesis for the origin of this complexity is the RNA world. In this model, the first self-replicating molecules were RNA strands, molecules that can both carry genetic information and catalyze chemical reactions. RNA is more versatile than DNA, which carries information but requires proteins to replicate it. If RNA could replicate itself and also catalyze the synthesis of more RNA, then it could in principle have bootstrapped biological complexity from purely chemical beginnings. The RNA world hypothesis has been developed in considerable detail and has experimental support. But the problem remains of how the first self-replicating RNA strand arose. An RNA strand needs to have a specific sequence of nucleotides to fold into a shape that allows it to catalyze its own replication. The information content required is not trivial. The probability of a functional self-replicating RNA sequence assembling spontaneously from random nucleotides in a prebiotic ocean is extraordinarily difficult to estimate reliably, but many estimates suggest it is very small. Various mechanisms have been proposed to increase the probability: mineral surfaces that could concentrate and align nucleotides, hydrothermal vents providing energy and catalytic surfaces, repeated concentration and dilution cycles in tidal pools, ice forming around prebiotic molecules to bring reactive molecules into close contact. Some of these mechanisms have shown promise in laboratory experiments, but we do not have a complete, experimentally verified, end-to-end account of how the first self-replicating molecule arose. We have pieces of a puzzle. We are not sure the pieces we have are even the right ones. The origin of life is genuinely unsolved, despite being studied intensively for decades. This is not a temporary state of ignorance awaiting a simple answer. It is a reflection of the genuine depth of the problem. And even if we solve the origin of life, that is only the beginning of the chain. After life's origin, the record shows roughly 3.5 billion years of single-celled organisms before multicellular life appeared in significant diversity. Single cells dominated the planet for most of its history. During this time, the cellular machinery of life was refined. The genetic code, the ribosome, the cell membrane, the metabolic pathways for energy extraction, the mechanisms of DNA repair and replication, all of these were innovations of the microbial world, worked out over billions of years of evolution. But during all this time, life did not become complex in the way we usually mean by that word. No nervous systems, no eyes, no locomotion beyond simple flagella, no multicellular coordination. Then, roughly 540 million years ago, something triggered what geologists call the Cambrian explosion, a geologically rapid diversification of complex animal body plans. In a span of tens of millions of years, most of the major groups of animals alive today appeared in the fossil record for the first time. Eyes appeared multiple times, independently. Limbs appeared. Nervous systems appeared. Predator-prey relationships appeared, driving rapid evolutionary arms races. The world went from single cells and simple mats of bacteria to something resembling a recognizably complex ecosystem in what is, geologically speaking, a brief interval. Why then? Why not earlier? Why not later? Why not never? These questions are still actively debated. Some researchers point to a change in atmospheric oxygen levels, suggesting that only when oxygen became abundant enough to support the high metabolic rates of active animals could complex life diversify. Others point to a cascade of ecological interactions, where the first predators drove the evolution of defensive structures like shells and harder bodies, which in turn drove the evolution of more sophisticated predators, bootstrapping complexity. Others suggest the development of certain key innovations in developmental genetics, tools for building complex multicellular bodies from a single fertilized cell that had to be worked out before the Cambrian could happen. None of these explanations is fully satisfying. The Cambrian explosion remains one of the great puzzles of evolutionary biology. Then another 540 million years of evolution, extinction events, continental drift, and climate changes, before anything capable of asking questions about the universe appeared. At least 5 mass extinction events reset the evolutionary clock to varying degrees. The event 66 million years ago, caused by a large asteroid impact in what is now the Yucatan Peninsula, killed the non-avian dinosaurs and roughly 3/4 of all species on Earth. It opened ecological space that allowed small, insect-eating mammals to diversify into the enormous range of forms they occupy today, including the primate lineage that eventually produced humans. Change the trajectory of that asteroid by a small amount, enough to miss the Earth, and the dinosaurs survive. The mammals remain a minor group of small nocturnal creatures living in the shadow of reptilian dominance. Perhaps, over the following 66 million years, some lineage of dinosaur would have evolved intelligence. But perhaps not. We have no way to know. What we know is that the specific sequence of events that produced us required that asteroid to hit, at that velocity, at that angle, in that location, 66 million years ago. A slightly different cosmic billiards game, and the story ends differently. Every link in this chain was an accident. Not one of them was inevitable. Remove any single link, and the chain ends in silence, somewhere far short of consciousness. You are not the destination the universe was heading toward. You are the improbable product of a sequence of accidents stretching back to the first quantum fluctuations of the inflaton field. The universe did not produce you on purpose. You are a statistical outlier in a cosmos optimized for nothing. And the fact that you can recognize this, that you can trace the chain of accidents backward and understand what you are, is the most extraordinary thing that has happened in the entire history of the universe. If the chain of accidents that produced us is so unlikely, there is a question that follows naturally. Is it possible that somewhere else in the universe, in one of the other 2 trillion galaxies, around one of the other estimated 10 to the 24 stars, on one of the other countless rocky planets in habitable zones, the same chain of accidents played out again? It is possible. It may even be likely, given the sheer number of opportunities. The Milky Way alone contains something like 100 to 400 billion stars. A significant fraction of those stars have planets. A significant fraction of planetary systems have rocky planets in habitable zones. The numbers are large enough that even a very small probability per planet produces a large expected number of planets where life could arise. But here is the thing. If intelligent life elsewhere in the universe is even remotely common, we should expect to see evidence of it. The galaxy is roughly 13 billion years old. The Earth is 4.5 billion years old. A civilization that developed even 1 million years before us would have had 1 million years of technological development before our species existed. In that time, a civilization with any interest in exploring or colonizing the galaxy could have spread to the nearest stars and then to their neighbors, and so on, in a chain of colonization that would eventually reach every habitable star system. At a modest fraction of the speed of light, perhaps 1%, a civilization could spread through the entire Milky Way in about 10 million years. 10 million years is a short time compared to the age of the galaxy. A civilization that began 10 million years before us could theoretically have settled every habitable planet in the Milky Way before the first land plants appeared on Earth. Yet we see nothing. We detect no artificial radio signals. We see no evidence of megastructures around stars. No Dyson spheres harvesting stellar energy. No artificial modification of stellar spectra. We find no artifacts in our solar system. No ancient probes. No evidence of visitation. The sky is quiet. The galaxy is dark in any wavelength where artificial signals would stand out. The silence is total. This is the Fermi paradox. First, articulated by physicist Enrico Fermi in 1950 when he asked his simple, devastating question, "Where is everybody?" The standard framing treats this as a puzzle. If intelligent life is common, we should see evidence of it. We do not. Therefore, something is wrong with our assumptions about the prevalence of intelligent life, or the behavior of intelligent civilizations, or our ability to detect them. Dozens of proposed solutions have been offered over the decades since Fermi asked his question. Perhaps intelligent civilizations destroy themselves before reaching the technological level needed for interstellar travel or communication. Nuclear war, engineered pandemics, runaway climate change, artificial intelligence, gone wrong. The Great Filter Hypothesis in its pessimistic form. There is a barrier that virtually every civilization hits and fails to pass, and it lies ahead of us in our future. If so, the silence is the sound of everyone who came before us failing, and we may be approaching our own failure. Perhaps intelligent civilizations exist, but have no interest in expansion or communication. Perhaps the default behavior of a sufficiently advanced civilization is withdrawal inward into virtual realities or into contemplative states that have no observable signature. Perhaps the universe is teeming with intelligence that has simply decided that the physical universe is not worth engaging with. Perhaps the distances are simply too large. Perhaps radio communication is not the right technology for interstellar messaging. Perhaps civilizations send signals we have not thought to look for, in frequencies we have not searched, encoding information in ways we have not recognized. All of these are possible, but there is a simpler explanation that fits everything we see. Perhaps the silence is exactly what you should expect from a universe where the chain of accidents that produces intelligence is so improbable that it runs to completion at most once or twice in the entire observable universe over the entire history of time. Consider how many filters the chain contains. The physical constants have to be right. That is either a selection effect from the multiverse or the deepest improbability in physics. The baryogenesis asymmetry has to be right. The inflaton fluctuations have to be right. The star has to be the right mass and the right generation. The planet has to be in the right orbit with the right size and the right moon and the right gas giant shield. Chemistry has to cross the threshold to self-replication. Multicellular life has to evolve. Intelligence has to evolve. A technological civilization has to develop without destroying itself first. Each filter individually may allow many planets through, but multiply the probabilities together. A 1 in 10 chance at each of 12 independent steps is a 1 in a trillion overall probability. A 1 in 100 chance at each of 12 steps is 1 in 10 to the 24. With 10 to the 24 star systems in the observable universe, a probability of 1 in 10 to the 24 means an expected number of 1 technological civilization in the entire observable universe. The numbers could work out to give us 1. They could give us 0. They could give us a handful. We do not know the probabilities at each step well enough to calculate reliably, but they could easily give us exactly the silence we observe. The universe is vast, yes. The number of opportunities is enormous, yes. But the universe is not obligated to be teeming with intelligence just because it is large. Large numbers of opportunities times vanishingly small probabilities can still give you a small or 0 result. The silence is exactly what the physics predicts for a universe governed by laws that make every link in the chain of complexity so difficult to forge. We should not be surprised by it. We should be surprised by ourselves. The James Webb Space Telescope has been searching for biosignatures in the atmospheres of exoplanets, chemical signatures that might indicate the presence of life. Specific combinations of gases that would be out of chemical equilibrium without a biological source, such as oxygen combined with methane, which rapidly react with each other and can only coexist if something is continuously producing them. Early results have been ambiguous. Some intriguing hints in certain spectra. No confirmed detection of life. More planets have been observed than ever before, and the silence in their atmospheres continues. The absence of detected life does not prove that no life exists elsewhere. Our search has been limited to nearby exoplanets, and only certain types of biosignatures in certain wavelengths. The universe is vast, and we have examined a negligible fraction of it in any meaningful way. A single confirmed detection of life, even microbial life in a nearby planetary atmosphere, would be one of the most significant discoveries in human history, completely reframing our understanding of how common the accident is. But the silence of the more advanced search, the radio silence across the galaxy, is harder to explain away. We have been listening for artificial radio signals for decades. The SETI program has scanned large portions of the sky at many frequencies. The Breakthrough Listen initiative has used some of the most sensitive radio telescopes ever built to search for artificial signals from nearby stars and from distant galaxies. The result is consistent silence. No signal that could not be explained by natural processes. No evidence of anyone out there. If technological civilizations are common in the galaxy, the radio silence is genuinely strange. A civilization that developed radio technology 1,000,000 years ago could have flooded the galaxy with signals by now. A civilization that developed sufficiently advanced technology might be detectable by other means, through the waste heat from their energy use, through the modification of stellar spectra, through the engineering of planetary environments. We see none of this. The most chilling interpretation, and the one that fits most naturally with everything we have discussed, is this. The reason we see no one is that there is no one. We are alone, or very nearly alone, in the observable universe. The chain of accidents that produced us ran to completion here, on this planet, around this star, and possibly nowhere else in the 2 trillion galaxies we can observe. If this is true, it carries an implication that is both terrible and magnificent. It means that we are, as far as we can tell, the only witnesses the universe has. The only part of the cosmos that is aware of itself, the only configuration of matter that looks up and asks questions about what it is and where it came from and where it is going, the entire intellectual and cultural heritage of humanity, every piece of knowledge ever accumulated about the nature of the physical world, may be the only such accumulation that has ever existed or will ever exist in the observable universe. This does not make us important in any physical sense. A single human being is vanishingly small compared to a star. The entire human population is negligible compared to the mass of a single asteroid. The biosphere of Earth is a thin film on a small rock, orbiting an unremarkable star in the outer region of one of 2 trillion galaxies. We are not large. We are not powerful by cosmic standards. We are not durable. We are not central. But if we are the only minds in the observable universe, then every thought that has ever been thought, every scientific discovery, every work of art, every moment of genuine understanding happened here and only here. The universe produced consciousness once, locally, temporarily. And that consciousness is us. Someday we will detect something, or we will not. If we detect life elsewhere, the accident was not unique, and the universe is somewhat more hospitable to complexity than the current silence suggests. If we never detect anything, the silence will be the most profound statement the universe has ever made about itself. I tried once, here, and then I was silent again. But if the silence continues, that too is an answer. And it is the answer the emptiness was always suggesting. Before we turn to the unraveling, let us sit for a moment with the accident itself. Not just its improbability, but its nature. What are we, exactly, if everything we have described is true? We are, first of all, patterns. Complex, self-maintaining, self-replicating patterns in matter. The atoms that make up your body are not you. They were not you last year, because most of them have been replaced through the metabolic processes that continuously break down and rebuild the structures of living cells. The specific carbon atoms in your muscles today are not the ones that were there a year ago. The water molecules in your blood will be somewhere else in weeks. You are not your atoms, you are the pattern those atoms temporarily instantiate. Patterns exist throughout the universe at many levels of complexity. A crystal is a pattern. A standing wave in a river is a pattern. A tornado is a pattern. A galaxy is a pattern. But these patterns are passive. They do not maintain themselves against disruption. They do not encode information about their own structure in a way that allows them to be reproduced. They do not respond to their environment in ways that preserve their own coherence. They just are. For as long as the physical conditions that produce them persist, and then they are not. Living patterns are different. A living cell actively maintains its structure against the entropy that constantly threatens to dissolve it. It takes in energy and materials from its environment and uses them to repair damage, replace worn components, and reproduce its own structure in new instances. A living cell is fighting thermodynamics every moment of its existence and winning temporarily. Every living thing that has ever existed has been an ongoing rebellion against the natural tendency of complex structures to decay into simpler ones. You are one of those rebellions, temporarily. You are a pattern of extraordinary complexity that has been fighting entropy since the first cell division that created you, using energy derived ultimately from the nuclear reactions in the Sun, which themselves derive from the gravitational potential energy released when the solar nebula collapsed, which itself derives ultimately from the slight density variations imprinted on the fabric of space-time by quantum fluctuations during inflation in the first fraction of the first second of the universe's existence. There is a direct causal chain from the quantum noise of the inflaton field 13.8 billion years ago to the fact that you are reading these words right now. Every link in that chain was necessary. Every link was contingent. None of it was inevitable. All of it happened. And beyond being a pattern, beyond being a rebellion against entropy, you are something stranger and rarer still. You are a pattern that has become aware of itself. You are a configuration of matter that has developed the capacity to model its own existence, to represent its own history, to project its own future, to understand, at least in outline, the physical laws that govern its own behavior and the behavior of the universe it inhabits. Consciousness is the most extraordinary product of the accident. Not because it is large or powerful or long-lived, because it is none of these things compared to the universe it exists within. It is extraordinary because it is the first thing in the history of the universe that has had an inside. A black hole does not experience being a black hole. A star does not feel its hydrogen burning. A galaxy does not know it is a galaxy. The universe, for most of its history, has simply been happening with no one inside it to notice. You are inside it. You notice. This is such a strange and improbable thing that it is worth dwelling on at length. The Big Bang produced a universe of hydrogen and helium plasma, expanding and cooling. That plasma gradually condensed into the first stars, which fused heavy elements and scattered them into space when they died. Subsequent generations of stars formed rocky planets from those heavy elements. On at least one of those rocky planets, in the right orbital zone around the right kind of star, in a galaxy at the right stage of chemical enrichment, chemistry crossed the threshold to self-replication. Self-replication led to evolution. Evolution led to multicellular life. Multicellular life led to nervous systems. Nervous systems led to increasingly complex information processing. And eventually, after 4 billion years of this, information processing became sophisticated enough that the patterns doing the processing could turn their processing capacity on themselves and recognize what they were. The universe became self-aware. Not the whole universe, a tiny local exception in an overwhelmingly empty cosmos. A brief temporary configuration of atoms on one small planet, around one ordinary star in one unremarkable galaxy, but self-aware nonetheless. The universe, through the mechanism of evolution and neurology, produced something that could look at itself and say, "This is what I am, and this is what you are, and here is the story of how both of us came to exist." This is genuinely unprecedented. For 9 billion years after the Big Bang, the universe expanded, and stars formed, and galaxies collided, and supernovae scattered heavy elements through the void, and none of it was witnessed by anything. None of it was understood. There was no inside to any of it. The events happened according to the laws of physics with perfect indifference, unobserved, uninterpreted, purely physical, purely external. Then, approximately 4 billion years ago on one small planet, the first cells appeared, and the universe acquired for the first time an inside. Somewhere inside the cosmos, for the first time, something was experiencing something. The light falling on a photoreceptor was not just physics, it was seeing. The chemistry of a cell wall maintaining its integrity against the osmotic gradient was not just chemistry, it was surviving. Something was happening for someone, rather than simply happening. And then, much later, that inside became reflective. The universe produced something that could turn the capacity for inner experience on itself and recognize what it was. That capacity changes nothing about the physics, but it changes everything about the meaning. This capacity changes something about the universe's history, even though it changes nothing about its physics. Before consciousness, the universe's history simply happened. Events occurred according to the laws of physics, but no one tracked them, no one understood them, no one gave them meaning. After consciousness arose, the universe acquired a witness. The Big Bang, which happened 13.8 billion years ago, is now understood, reconstructed from indirect evidence, communicated between minds, incorporated into a story that minds can hold and pass on and build upon. The universe did not know about the Big Bang until minds arose to reconstruct it. In a real sense, minds did not just emerge from the universe. Minds gave the universe a past it could not have had without them. Because a past that is never known by anyone is indistinguishable, in any meaningful sense, from a past that never happened. This is not mysticism or metaphysics. It is a straightforward observation about the role of information in physical reality. Information is not independent of minds. It requires a system capable of reading it. The universe's history is encoded in the physical structure of the present, in the cosmic microwave background, in the distribution of galaxies, in the composition of stars, in the geology of planets. But encoding is not the same as information. Information requires a reader. We are the readers. We are the part of the universe that reads itself, and this reading is fragile. It exists in biological tissue, sustained by metabolic processes on timescales of years and decades. When the last mind goes out, whenever that happens, the universe's knowledge of itself will be lost. The equations will not persist anywhere. The understanding will dissolve as completely as if it had never existed. The universe will return to being a physical process that happens without a witness, without comprehension, without an inside. But it has not happened yet. Right now, the universe has a witness. Right now, there are minds reading it. And the fact that this brief, improbable, unrepeatable condition exists at all, the fact that the chain of accidents ran all the way to completion, the fact that matter learned to think is the single most remarkable thing that has happened in the entire 13.8 billion year history of the cosmos. The accident is not stable. This is perhaps the most important thing to understand about our situation. Not only did we arise by a chain of improbabilities that we are still struggling to understand, but the conditions that made us possible are themselves temporary. The universe is not settling into a stable state that will persist indefinitely. It is actively moving toward a state in which nothing like us can exist. The emptiness is not static, it is advancing. Let us start with what is already underway. The acceleration of the universe's expansion, driven by dark energy, is not a future event. It is happening right now, as it has been happening for billions of years. The expansion rate is increasing. Every second, more space comes into existence between us and the distant galaxies. The effect is not noticeable on the scale of our solar system, or our galaxy, or our local group of galaxies, because gravity holds these structures together against the expansion. But beyond the local group, every other collection of galaxies is already receding from us, and the farthest ones are receding faster than light can travel through the expanding space between us. In about 150 billion years, the expansion will have carried all galaxies beyond our local group past a horizon from which their light can never reach us, even light emitted today that has not yet arrived. After that point, even if a civilization in a distant galaxy sent a message traveling at the speed of light right now, that message would never arrive. The universe will be partitioned into isolated bubbles, each one unable to communicate with or even observe any other. Future astronomers in that distant era will look up at a sky containing only the merged remains of the Milky Way and Andromeda, surrounded by an otherwise empty void. They will have no way of knowing that the universe contains other galaxies. The evidence will be gone, carried beyond the horizon by the expansion. This is already the fate of most of what we can currently see. The galaxies we observe with our telescopes today are, in a meaningful sense, already gone from our future. We are seeing them as they were billions of years ago. Their current reality, whatever it is already permanently beyond our reach. We are archaeologists of light, reading records from a universe that no longer exists in the form we can see. And beyond the isolation driven by expansion, there are more dramatic possibilities for how the accident ends. The Higgs field permeates all of space. It is the field responsible for giving mass to fundamental particles. It has a specific value throughout the observable universe, one that has been measured at the Large Hadron Collider through the mass of the Higgs boson, approximately 125 GeV. That measurement places the Higgs field in an interesting and alarming position. Calculations based on this measurement suggests that the current state of the Higgs field is not the lowest possible energy state. It is a metastable state, technically stable for now, but not at the absolute minimum of its potential energy. Physicists describe this as a false vacuum. The true vacuum, the actual minimum energy state of the Higgs field, is lower than where we currently sit. Like a ball resting in a small depression partway down a hill, the universe is stable against small perturbations, but vulnerable to a quantum push of sufficient size. The push, in this case, comes from quantum tunneling. In quantum mechanics, particles can tunnel through energy barriers even if they do not have enough energy to go over them classically. Applied to the Higgs field, this means there is a small but non-zero probability that the field can spontaneously shift from its current metastable state to the true vacuum state. This would nucleate a bubble of true vacuum, a tiny region of lower energy physics, expanding outward at the speed of light. Inside the bubble, the laws of physics are different. The masses of fundamental particles would be different. The electromagnetic force would have a different strength. Atoms as we know them could not form. Chemistry as we know it would be impossible. Everything the bubble engulfs is not destroyed in any conventional sense. It is remade by different laws of physics, laws under which nothing resembling what existed before can persist. The bubble expands at the speed of light. There is no warning because nothing can travel faster than the bubble front. You would not see it coming. You would not feel anything. One moment the laws of physics would be what they have always been, and the next moment they would not be, and there would be no transition state between existence and non-existence. This might have already started. A vacuum decay event could have nucleated billions of years ago, somewhere in a distant galaxy cluster, and the expanding bubble could be racing toward us right now, billions of light years away. We would have no way to know until it arrived. And by then, knowing would be irrelevant. The probability of vacuum decay in any given region of space, in any given year, is extraordinarily small. The universe's apparent survival to its current age tells us the probability per unit volume per unit time is very low. It does not tell us the universe will survive forever. Whether vacuum decay occurs eventually depends on whether the probability is truly zero or merely very small. Current calculations suggest it is very small, not zero. Over long enough timescales, very small probabilities become near certainties. If the vacuum does not decay, the universe ends more slowly and more quietly. Star formation will continue for roughly 10 to 100 trillion years, as long as cold gas remains in galaxies to collapse into new stars. The last stars to form will be small red dwarfs, burning for trillions of years before finally exhausting their fuel. The stelliferous era, the age of stars, the era we currently inhabit, will eventually end. The last red dwarf will burn its last hydrogen and go cold. The universe will go dark. Consider what that transition means. For 100 trillion years, the universe has contained light. Starlight falling on planetary surfaces, photons bouncing between gas molecules in stellar atmospheres, radiation streaming outward from billions of fusion reactions. Light has been the constant companion of matter since the first stars ignited. When the last red dwarf goes out, the darkness will return. This time permanently, and vastly deeper than before. There will be no starlight anywhere, in any direction, for any observer who might somehow exist to look. The degenerate era that follows will last vastly longer than the stelliferous era. White dwarfs will cool to black dwarfs over trillions of years. Neutron stars will spin down and go cold. Galaxies will dissolve as gravitational interactions fling stars into intergalactic space or spiral them into central black holes. The universe will be a dark, cold collection of stellar corpses drifting further apart in an expanding void. Occasionally, rare collisions between black dwarfs will trigger brief supernovae, brilliant flashes of light in an otherwise completely dark universe. But these events will be extraordinarily rare, separated by vast stretches of absolute darkness. If protons decay, as some theoretical models predict, even those stellar corpses will eventually dissolve. Over timescales of 10 to the 34 to 10 to the 40 years, protons would spontaneously transform into lighter particles, emitting a faint glow of radiation as they do. Black dwarfs, neutron stars, cold planets. Every object made of ordinary matter would slowly evaporate, converting to a thin gas of electrons, positrons, photons, and neutrinos. The era of ordinary matter would end not with a bang, but with a very slow, very quiet hiss spread across timescales so long that the entire age of stars fits within the first moment of the clock measuring them. Black holes survive because they are not made of protons. They are concentrations of space-time curvature. But black holes have a finite lifetime through Hawking radiation. The process is extraordinarily slow. A black hole with the mass of the Sun takes 10 to the 67 years to evaporate. A supermassive black hole takes up to a Google years, 10 to the 100. As a black hole loses mass, it shrinks, gets hotter, radiates faster, until the final stages, when what has been patiently radiating for a Google years releases the last of its mass in a brief, intense burst lasting less than a second. After a Google years of near-perfect silence, a flash. And then, nothing. After the last black hole evaporates, the universe contains no massive structures of any kind. What remains is a thin gas of photons and neutrinos, expanding through an increasingly enormous space, cooling toward absolute zero. The photons carry essentially no energy. The temperature approaches absolute zero asymptotically. The universe has reached the state that thermodynamics has been pushing it toward since the Big Bang. Maximum entropy, the final silence. And yet quantum mechanics does not stop. Even in the most boring possible configuration of the cosmos, the laws of quantum mechanics continue to operate. Quantum fields still fluctuate. Given enough time, random quantum fluctuations will eventually produce any configuration of matter that is physically possible, no matter how improbable. A rock, a planet, a star, a brain. Not a brain evolved over billions of years. A brain that spontaneously assembles directly from the background radiation through a quantum fluctuation, complete with false memories that feel real, complete with sensory impressions that seem to correspond to a world. This brain exists for a fraction of a second, and then dissolves back into the thermal background. These are Boltzmann brains. They are a genuine theoretical prediction of statistical mechanics applied to an eternal universe. The timescale for such a fluctuation is almost incomprehensibly long, something like 10 to the 10 to the 50 years, a number that makes the Google year black hole era look like a single morning. But in an eternal universe, this timescale is eventually reached, and over infinite time, the number of Boltzmann brains that spontaneously assemble and dissolve is not small. It is infinite. This raises a question that has not been satisfactorily answered. If the universe produces infinitely many Boltzmann brains over infinite time, and only a finite number of evolved biological observers like us, then a random conscious observer is infinitely more likely to be a Boltzmann brain than a biological one. But you do not experience yourself as a Boltzmann brain. Your memories seem continuous, your sensory impressions seem coherent. A Boltzmann brain would experience exactly the same thing. its false memories would feel exactly as genuine as yours do to you. From the inside, there is no difference. You cannot prove you are not one. The physics does not give you the tools to prove it. The resolution of the Boltzmann brain problem, if there is one, probably requires that the universe does not in fact last forever. If vacuum decay terminates it before Boltzmann brains become statistically dominant, the problem dissolves with the universe. If there is something fundamentally wrong with how we are applying statistical mechanics to an infinite universe, the problem dissolves with our assumptions. Physicists are working on it. There is no clear resolution yet. In the meantime, the universe continues its long, quiet journey toward a silence so complete that even the concept of waiting for something to happen becomes meaningless. Time passes. Nothing changes. The thread of improbability has run its full length. The void, patient as always, has the last word. Let us come back. We have traveled a long way tonight. From the quantum fluctuation that should have vanished to the heat death that will not be avoided. From a universe of near-perfect emptiness in which an extraordinary sequence of contingencies temporarily produced structure, chemistry, life, and the ability to ask questions about all of it. We have been honest about what the physics says, without softening it or dressing it up in false comfort. The universe is almost entirely empty. The matter that does exist is a thin residue of a baryogenesis asymmetry we do not fully understand. The laws of physics that allow atoms to exist are balanced on a knife edge whose origin we cannot explain. The thread of contingencies that produced life on Earth required every link to hold. The thread that produced consciousness required billions of years more. The silence of the cosmos suggests we are alone in having run it all the way to its end, or nearly so. And the physics of the future ensures that the thread will eventually break, that what was temporarily assembled will be disassembled, that the void will reclaim what it lent. This is not easy to sit with. It was not designed to be. The universe does not owe us comfort. But consider what this improbability actually achieved. 13.8 billion years of compounding contingency produced something that can contemplate its own contingency. Something that can trace the whole story backward to the quantum fluctuations of the inflaton field and forward to the evaporation of the last black hole. Something that can calculate the timescale for proton decay and project the arc of the universe from its first moment to its final silence. Something that can feel the weight of all of this and ask what it means. The void does not care about any of this. It cannot. Caring is something only the improbable can do. The universe does not have a perspective on itself. It does not experience its own vastness, its own age, its own emptiness, its own beauty. It has no inner life, no awareness, no curiosity. It simply is. The stars burn without knowing they are burning. The voids expand without knowing they are expanding. The black holes evaporate without knowing anything at all. You are the part of the universe that knows. You are the contingency that turned the universe into something that can look at itself and say, I see what this is. I understand the physics. I can trace the story from the Big Bang to the heat death. I can feel the loneliness of the Boötes void and the violence of the first supernova and the improbability of the Cambrian explosion. I can hold all of it in my mind simultaneously and understand that it is beautiful and terrifying and real. That is not nothing. That is the single most extraordinary thing that has happened in the entire history of everything. There is a question that sometimes gets asked about the significance of all this. Does impermanence diminish meaning? If the universe is going to end in a heat death anyway, if consciousness is temporary, if the sun will eventually swallow the earth, and the Milky Way will eventually dissolve, and the last black hole will eventually evaporate, does any of what happens between now and then matter? The argument that it does not is straightforward. In the long run, nothing persists. All structures dissolve. All meaning that is not written into the permanent fabric of the universe is temporary. And since no meaning is written into the permanent fabric of the universe, which has no such thing as a permanent fabric in any metaphysically loaded sense, all meaning is temporary. And temporary meaning is, on this view, no meaning at all. But this argument has a flaw. It assumes that meaning requires permanence, that a conversation between two people matters only if it persists forever, that a moment of genuine understanding is worthless unless it is recorded in some eternal ledger. That beauty is only real if it lasts. This seems wrong. A piece of music is not rendered meaningless by ending. A conversation is not rendered pointless by concluding. A life is not robbed of significance by death. The value of an experience is not determined by its duration. It is determined by its nature. A brief, intense experience of genuine understanding, of genuine beauty, of genuine connection, has value that is not reduced by the fact that it ends. The ending is part of the experience, not a negation of it. The universe produced you. It produced the capacity to understand the universe, to feel awe at its scale and its emptiness and its improbability. That capacity, however temporary, is real. It is happening right now, and the fact that it will eventually cease does not make it less real now. It makes it more precious. The stelliferous era, the brief bright window when stars burn and chemistry happens and minds can exist, is not less valuable for being temporary. It is more valuable. It is the only window there will ever be. The thermodynamics was settled at the Big Bang. Entropy has been increasing ever since, and it will continue until there is nothing left to increase. The void was always going to outlast everything it produced, but it has not outlasted it yet. Right now, in this moment, you are alive in the window when the improbable thing is still running. The stars are still burning. The voids are still surrounded by thin filaments of light. The cosmic web still has structure, gradients, complexity. Chemistry still happens on at least one planetary surface, and possibly on others we have not yet found. Minds exist that can trace the full arc of cosmic history and feel the weight of where we are on that arc. The window is finite. The last red dwarf will burn its final hydrogen in about 100 trillion years. Before that, the sun will have swollen into a red giant and ended any possibility of life on Earth in about 5 billion years. Before that, our civilization will face challenges we cannot currently predict. This is temporary. It always was. But right now, it is still happening. The universe has not yet finished dreaming. When you look at the night sky tonight, you are not looking at a permanent backdrop. You are looking at temporary fires burning through a fuel supply that will eventually run out, in galaxies that are slowly drifting beyond reach, in a universe that is heading toward a silence that will make the current quiet of intergalactic space seem like noise. The stars, you see, are the exception. The darkness between them is the rule. And you are a smaller exception still, a flicker of awareness in a universe that overwhelmingly prefers the dark. But here you are, against all probability, against the natural direction of everything, here you are, aware, curious, looking up at the stars and knowing what they are, and knowing what will become of them, and knowing despite everything that the fact of your knowing matters. The emptiness was here before us. It will be here after. And for one brief, impossible, unrepeatable moment in between, it looked back.